outline is the following. I will first, you will not be terribly surprised that I bring some criticism of Sugden's induction-based approach. And first we discuss in more detail what is induction, and then I discuss Sugden's use of induction, and then we'll see whether that works or not. And then I will present an alternative approach, the explanation in the model world, and that's somehow different. I go into more detail in the explanation of the model world, and then to the transfer to the real world. Okay, so the first question is, what is induction? I did something in the first lecture or second lecture already, or first lecture in this class. What is induction? First, for contrast, what is deduction? Okay, deduction, the example that's 2,500 years old. Socrates is a human being. All human beings are mortal. Therefore, Socrates is mortal. This is deduction, right? And the fundamental thing about deduction is compelling inference. So it's absolutely mandatory. You can't avoid it. If you accept the premises, you've got to accept the conclusion. There's no alternative to that. The conclusion is necessarily true if the premises are true. So there is, I call it the truth transfer. There is, in a logical deduction, there's a sort of truth transfer. The truth that sits in the premises is transferred to the conclusion, necessarily. Nothing gets lost. Right? So this is deduction, and this is necessary to understand that in order to understand the difference to induction. Now, an example of an inductive step is an example which I used already. Piece 1 of copper conducts electricity, piece 2 of copper conducts electricity, piece 3 of copper conducts electricity, and you have some finite sample of these pieces of copper, and then you make the inductive step. All pieces of copper conduct electricity. It's just the inductive generalization. So what's the difference to deduction? In contrast to deduction, the inductive step is risky. Right? It doesn't always work. It can be false because it generalizes from a finite number of cases to all cases, right? And there's no guarantee that this works. Sometimes it does, sometimes it doesn't. And a very useful term to remember here is that inductive inference is ampliative, right? The conclusion states more than the premises. Right? In that the conclusion is richer, it says more than in the premises. And that's, of course, that's not necessarily then true if the premises are true. Whereas in the deduction, it's so that the conclusion does not start more than the premises. It usually states less. But it's such that it states the same stuff that's already contained in the premises. So if you believe the premises, you have to believe the conclusion. But that's different in the inductive inference because the inductive inference is ampliative. Deduction is non-ampliative. So that's really to have, I have that always in the back of my mind. The conclusion is just richer than what's in the premises. So you can't get a guarantee for its truth if you know that the premises are true. Okay. So remember from section 2, I distinguished two different problems of induction, and that's important for the following. The philosopher's problem of induction is the following. If the inductive step is plausible, for instance, in the copper case, what is the justification of the inductive step? Right? One thing is that it works, and the other one is that you say, I can justify why it works. I understand why it works. Right? This is the philosopher's problem. And, well, many philosophers believe that this problem of induction is unsolvable. For 250 years, the discussion has been going on. There's just recently, again, some philosopher who said, I have solved the problem of induction. Right? We'll see how successful he will be. So it's still under scrutiny. It's very funny. It's one of these problems, you know. So that's the philosopher's problem of induction. And remember, it's different from the scientist's problem of induction because the scientist is happy when induction works. And he wants to find those cases in which it works in contrast to those in which it doesn't work. Distinguish the cases in which induction works from those in which it doesn't work. And here's a case where it works. 10 pieces of copper conduct electricity, therefore all pieces of copper conduct electricity. That's a fundamental, wonderful case. But versus this one, 10 coins in my pocket are made of copper, and then you conclude all coins in my pocket are made of copper, right? You've got 20 coins in your pocket, you know, they come in any sorting, and then you take out 10, and then you have 10 are made of copper, and then you conclude all of them. Yeah, in many cases this won't be true, right? Because you have a Swiss franc in between, which is not made of copper, hopefully. All right. Okay, so in these cases it doesn't work, or the falling from the Empire State Building is another one, right? 30 stories, 40 stories, happy days, and then after 100 stories, stories over. Now, what's the difference between these two cases? Now, when we analyze it in the following terms, something may become clear. Well, we would say that it's a natural law that copper conducts electricity. And once you hit upon a natural law in a few cases, you can generalize to all cases. So when you do the same now with a different metal, say with iron, and you know there are natural laws, about copper that it conducts electricity, and then you come to iron and you have a few items of iron, they all conduct electricity, you say, well, probably there's also this natural law that iron conducts electricity, right? It's not just an accident because metals have something to do with electricity, and therefore, and then it becomes plausible why that inductive inference works. If you hit upon a natural law, then you get, by the natural law, you're getting the license, to generalize. The question is, how do you know it's a natural law? That's a different story. But if you have some confidence you hit upon a natural law, then generalization works. So if you could presuppose that the world is full of natural laws, then the question is to find them out and then generalize. Anyway, how that works is a different story. Then we're back in the philosopher's code. But just to understand that, if a natural law exists, but the regularity of the first 10 coins in my pocket is purely accidental. There is, so to speak, nothing behind these facts. If you just look at this, there's nothing that would give a basis for the generalization. Therefore, the generalization doesn't work. So in most cases, you will have also, if you have 50 coins in your pocket or 20, there will be other coins not made of copper. And therefore, you cannot generalize. And the scientist's job who wants to use induction must look, if you have a certain case in which you want to generalize, is it of the first kind or the second kind? Is there some sort of regularity behind it, or can you have at least the suspicion, or you can believe there is something behind it? But in certain cases, there's nothing behind it, and therefore generalization is impossible. Now, how does one know whether in a given case there is something like a natural law behind a given regularity making an inductive step work? That's, of course, the crucial question. As a scientist, when you say, is there whoops, what do we do? Well, natural laws always speak about one particular kind of objects. Right? It's a particular kind of objects that are the subject of a natural law. For instance, pieces of copper, when you speak about their conductivity for electricity. Or masses. Remember the free fall, law of free fall. These are all masses, and all masses somehow behave similar, in these conditions that the law of free fall discusses. Falling bodies, chemical substances. So when you have a chemical substance, an element, or also a compound, then all the samples of it, like copper also, all the samples behave the same. They are the same kind. And it's that being of the same kind that is the basis for similar behavior or equal behavior under the same circumstances, meaning some regularity that may have a law-like character. And this is often expressed as this: natural laws hold for natural kinds. Things that belong naturally together by having fundamentally the same properties. And once you hit upon a few representative of this natural kind, then you can generalize to the whole natural kind, because they all belong, in a natural way together. It's very difficult to say more about that, but intuitively I think it's very clear that once you have, like things that are so similar, like all copper pieces among each other, that you can then generalize. But you cannot do it for something that is by pure accident happens to be in my pocket, namely 20 coins, and then I take 10 out of them. That doesn't give you any information usually about what the other 10 coins are doing, because it's pure accident how they sit there. They don't form a natural kind of any kind, right? So, all right. So, the idea then is, if objects form a natural kind, they do so by their very nature, what they are, right? They are fundamentally the same, and therefore they obey the same natural laws, and therefore we can inductively generalize within a natural kind. And it's important here to say, within the natural kind. So you have the big natural kind, you get a few examples, a few samples of it, of individual members of that kind, and if you are confident it's a natural kind, then you are confident to generalize within the natural kind. So this is not really a solution to the problem. It just shows you that inductive reasoning is similar or is intimately connected with identifying natural kinds. It's more or less two sides of the same coin. It's identification of natural kinds. There are other ways how to describe that, but this is a way how we can understand induction. All right. Now, if you believe that all copper pieces conduct electricity, you have assumed that all pieces of copper or of metal form a natural kind. Right? This is more or less the same, that you're saying I can inductively generalize, or they are a natural kind. If you believe that all swans are white, you believe that white swans form a natural kind, which they do not. Right? I mean, whiteness is not something essential to swans. There are black swans as well. And this is now why Sugden rightly speaks in this context of some relevant or salient respect in which x1 to xn, these are my copper pieces, are similar, or of some significant similarity as a basis for induction. That's just right. And you can make it a little more precise, a little more sharp by saying, what he means is saying that this similarity, this fundamental similarity, or this relevant respect or salient respect is the basis for these objects forming a natural kind, and that then justifies to some degree inductive inferences. Okay, so this is Sugden's view of induction, which is basically correct about this salient, relevant similarity as the basis for inductive inferences within that natural kind. Now, Sugden's question is, again, how is the step made from a particular hypothesis true in a model world to the truth of that hypothesis in the real world? Namely, for instance, weak racial preferences lead to segregation, okay? And there he says then, now, yes, according to Sugden, the step is inductive, which sounds perhaps plausible. It's a sort of generalization from the models to the real world. And then he got to say, you got to find now the significant similarity. If there is a causal factor F, both in the model world and in the real world, then F creates a significant similarity between the two worlds, right? The same with the copper pieces, right? You've got to identify, say, yeah, you've got to have an argument why they form one natural kind. And there he says, yeah, I find something very significant here that's both true in the model world and applies in the real world. And that's then the basis for my inductive generalization. And it must be, he says, a causal factor if I find that. And then this significant similarity licenses an inductive generalization from the model world to the real world, right? And the causal factor is, of course, here fundamentally the weak racial preferences plus the dynamic that comes there, because that's a causal factor for the development in the model world. That's a causal factor in the real world. And then he says, look, we have the same causal factor in both cases, model world, real world, and in the model world we can calculate it, and therefore we can inductively generalize to the real world. Yeah? Okay, so he's just showing on which basis the inductive step is possible. If causal factor F explains regularity in the model world, then it can be generalized that F also explains R in the real world. So he's seemingly doing exactly that. So if something is copper in my 10 pieces here, and then I show, yes, this copperness, this really produces electric conductivity, and then I say, okay, then I can generalize to other pieces of copper that I identify as copper, and then I know they will also conduct electricity. So it seems to be a perfect inductive inference. All right? It seems to be, all right? Now, normally inductive generalizations works from some cases of X to all cases of X, and all cases of X form a natural kind, copper pieces, right? That's the normal case of induction. And this one is a little different that Sugden discusses. Here the case is different. Sugden wants to infer from model cases to real cases. But he says, yeah, this difference between model and real isn't so important because the causality is the same, and that produces the natural kind. And therefore, Sugden wants to argue that real cities of a particular kind and specific theoretical models form one single natural kind, namely the union, right? The model cities and the real cities. They are one natural kind. The relevant models as instances of some category some of whose instances actually exist in the real world. So he uses the term category that can be replaced by natural kind. We have a natural kind, right? And some of the cases, some of the elements of that natural kind are model worlds, and the other one are real worlds. So it's the real world. So you just like that? Well, let's see how good that is. Okay, this is the reasoning here, that real cities and specific theoretical models form one natural kind. And this then license the inductive inference from one of its subsets, namely from the model cities, to the other one, namely real cities. Right? If they form one natural kind, the same with the copper pieces. If these 10 ones, right, they are part of a larger natural kind, and then if you take these 10, you can then generalize. But if you started with the different ones, different subset, it would work as well. They're just one natural kind, right? They're all alike in a fundamental respect. That's the idea of a natural kind that licenses then inductive generalization. Okay. Now, Sugden argues for a significant similarity between Schelling's model cities and real cities regarding the causality at work. This is the idea, right? Because he says, yes, this causality in the dynamics of the model produces then segregation, and it is credible that for the same effect in the models and in reality, the same causes are responsible. Right? This is the inductive step, and the cause is then this weak racial preferences, and that produces everything in the real world. Thus, in effect, Sugden argues that the identity of causes and effects of model cities and real cities constitute their common membership in the same natural kind. Right? Although model cities are something very different from real cities, but because there's exactly the same causality, therefore they form a natural kind, and therefore I can inductively generalize with respect to this causality stuff. Right? This is the idea. Sounds quite convincing, doesn't it? This, in turn, licenses the inductive step from models to reality. Right? This is the idea. However, now here comes my objection. In the model world, the real causal factors are completely different from the ones in the real world, contra Sugden. I think Sugden is fundamentally wrong here. He's really fundamentally wrong. And it's a mistake we saw already much earlier in other economies. In the model world, there is a representation of causal factors of the real world. Right? It's right that the causality in the real world is in the models, but only represented. It's not really there. And to show you that difference, I give you another example. Compare the forces that keep a real ship afloat with the forces that in a picture keep a ship image above the ocean image. Right? In both cases, there's a ship afloat. In the one case, it's Archimedes' law for swimming bodies. In the other cases, it's just that the color sticks to the canvas, right? And the ship color particles stick to the canvas, and the water image particles stick to the canvas. And because they stick there, the ship doesn't fall down into the water. So the causality is utterly different. It's completely different. It's something completely different. Although the image represents the causality of reality, right? It stays there. The ship in the image stays up above the water, and in reality, the ship stays up the water. But the causality is utterly different, completely different. And that's the same if you look a little closer in the model. The real causality in the model world is, if you have the model world on computers, is the electrons of the computer that executes the program. Right? That's the real causality. This is why different effects come, because you have electrons there and you have got the hardware and the software, and that then regulates that in the same way that they may represent the causality of the real world, but the causality itself is utterly different. It's something completely different, right? The same as in the ship image and the real image. So it's false that it's the same causality. And we had the same problem when we discussed Horstman's stuff. The question whether something is a real effect, it was the constraints on decisions and the beliefs about the constraints. And they are utterly different and have different effects, right? One thing is the real thing, and the other thing is the belief about the real thing. And they are utterly different, although the subject matter is the same, right? Or in a sense. So this is the same here, and he doesn't, as Horstman hasn't seen that in all clarity, that these are two utterly different things, and the representation of something is physically, so to speak, completely causally different from the thing itself, right? Not necessarily. I mean, if you have a representation of something just exactly with a scale of 1 to 10, then the causality may be identical, right? They are then the same causality, but not in these cases where we have a model, yeah? No, that's irrelevant. All I'm saying is the image with the ship is the idea is that it looks as if the causality of the swimming ship is the same in the representation and in the reality, and that's not the case. This is all I'm saying. And what he is doing with the models is exactly that sort of step. He says the relevant identity or similarity between the model world and the real world is the same sort of causality, and that's not true. That's false. The causality in the model world is done by the electrons, you know, how they jump around in the computer. The representation is something else, but you cannot from the representation. It's just not a natural kind, right? That the real things and the natural kind. So if you have copper pieces here, and here you have images of copper pieces, and you write the copper piece 1 and 2 and 3, but that doesn't conduct electricity, these images. Right? It's a completely different thing, right? Completely different. No way to inductively generalize. Okay? So the step in the model world to the real world can certainly not be an inductive step based on the identity of causal factors. That is certainly not possible. You must come up with a very different argument, but that argument certainly doesn't work. And this is really the core of Sugden's argument. It's really the identity of the causal situation. And I can show you now, well, as he correctly states, models at least form a parallel reality, but with happily, and this is now my addition, with utterly different causalities. Right? The causality in the model world is utterly different, although it may represent that causality, but that's something else. A representation of something is something else as the real thing. If you happen to have a partner that who lives far apart from you, it's really a difference whether you look at her or his picture or he or she is present, right? You can also hug the picture, but that's different from hugging the real person, right? The causalities are very different, also in these cases. It's a difference between representation and reality, right? And you may sometimes learn something in one way from the other, in both ways, but certainly not because of the similar causality. All right. So, now, and I show you now that he's really, in a sense, well, he's making a trick. Sugden masks the implausibility of the inductive step by the following rhetorical trick, and you find that trick if you follow exactly what he's saying. He starts with a plausible assumption, namely large industrial cities in northeast of United States featuring racial segregation form a natural kind, licensing inductive inference to the next case, for instance, to Cleveland. So you have 10 cities in the United States, right, and you find there weak racial preferences, and segregation, and then you say, okay, what's happening in the next one? And if you find there also weak racial preferences, you can say, generalizing from the 10 cases to the next one, right? And say, yes, I can expect there racial segregation as well. This is a rather plausible inductive step because they form really a sort of natural kind, at least, yeah, in some weaker sense, they form a natural kinds because they are all large cities in this area with similar socio-cultural, economic conditions and so on. Okay, so then he says, Sugden redescribes 24 in the middle. Each city constitutes a model of the forces at work in large industrial northeastern US cities, a natural model. So he redescribes that and says, here we have the natural kind, right? And each one is a model of that natural kind. This is how he describes it. It's his words. A natural model, not an artificial, a natural model. Now, this is a rhetorical trick. Normally, one would call every single case an example of the forces at work, or an instance, and not a model, right? You have these forces, you wouldn't say it's a model of that, that's very unnatural. So why is he doing that? Okay, I can show you exactly. Why does he employ this trick? Now, but if we can make inductive inferences from natural models, why not from theoretical ones? Right? So he's building up something new. He says, oh, we have different kinds of models. We have natural models and we have theoretical models. Okay, Now we can make inductive inference from natural models. You know, this was the generalization to Cleveland. And they say, okay, but they're all models. Okay, therefore we can also generalize from theoretical ones. And this is a suggestive rhetorical question which exploits the replacement of example by natural model and its implied assimilation to theoretical model, right? This is a rhetorical question. The answer, you say, of course, yeah, if I can make inferences, inductive inferences from natural models, sure, then I can also make inferences from theoretical models. This is what he's suggesting, right? And that works only, you know, because he uses the term natural model here. The above rhetorical question loses all its suggestiveness once you replace model by the much more appropriate term example, the original term, and then the sentence reads, this sentence reads, you replace why not from theoretical models, natural models, why not from theoretical models, but if you can make inductive inferences from examples, why not from theoretical models? Absolutely no reason. Yeah? So that's the trick. By redescribing a concrete example by natural model, you get verbally something, the class of pseudo-class of pseudo-natural kind of models, right? There's natural models, theoretical models, and then, of course, we can inductively generalize. But that's a rhetorical trick. And, of course, if you see this one, well, if I can make inductive inferences from examples, namely concrete examples of American cities to the next city, this doesn't listen anything about models, right? It's completely implausible. But he masks that, and that's really a rhetorical trick. I don't know whether he's aware of it, but it's certainly a rhetorical trick. And you see that immediately if you take the natural models here out and use examples, then you see immediately it's completely implausible, right? We are at the beginning. It doesn't answer anything, so it's purely rhetorical. So this is really strange. Okay. So you see here how, so to speak, the mechanism is used, that we are tricked into belief that this is somehow credible, right? I guess Sugden believes it himself and thought this was a good move. But I say it's a rhetorical trick because the basic fallacy is really that he thinks that the same causality is at work in both cases, and that is not the case. This is just false. All right? Now the conclusion is this. Induction works where it works only within natural kinds, due to some fundamental homogeneity among their elements. For instance, the copper pieces. Their induction works, but only within that class. There is no fundamental homogeneity between this constructed set of Sugden, the model cities, united, this and between this one and the real cities created by a common causality, such that we can exploit it in inductive inferences. Their causality is utterly different, although one may represent the other one, but that's a different story, right? Thus, the step from model cities to real cities cannot be inductively justified. It doesn't work that way. It must work anyway, but not this one. Okay, so